Okay, so welcome back, and we want to now consider how are we going to fit the logistic model, or how are we going to derive values for the coefficients from our logistic regression model. Now, in linear regression, we use the method of least squares to estimate the parameters beta 0 and beta 1. And if you recall, in the method of least squares, we consider the sum of the square deviations of each of the response variables about the predicted values for the response variable. And we are going to choose, and the beta 0 and beta 1 are part of the model. So we're going to basically choose the values of beta 0 and beta 1 that minimize the sum of the square deviations of the response variables to the predicted values based on the model. And under the usual assumptions for linear regression, when you get these least squares estimates, they yield estimators with a number of desirable properties, like, for example, that they're unbiased and the minimum variance in the class of all unbiased estimators. So this, unfortunately, if you try to apply the method of least squares to a dichotomous outcome variable, the estimators won't have these properties. So what we have to do, and by the way, what they don't tell you when you study linear regression, is that in linear regression, when you use the method of least squares, you are getting maximum likelihood estimates as well. But they don't really ever tell you that. They just say you're going to get least squares estimates, but you're also getting the maximum likelihood estimates. Now, many of you may have heard the term maximum likelihood, but my experience is that even if you've heard the term, you probably don't understand maximum likelihood very well. So I want to take a few minutes to review with you what maximum likelihood estimation is about and how it works and what the process is here for linear regression. So I'm going to go to the whiteboard, and I want to consider a situation where we're going to build the structure for maximum likelihood estimation. So let's say that an alien from outer space came down and landed in your home village, and the idea for this alien was that he or she or it was going to collect data on whatever they saw in your village. And one thing they noticed was that there were basically two types of people. And they didn't have words for males and females, but they were males and females. And usually the observer could tell the difference. Not always, but most of the time they could tell the difference. So one of the pieces of data they're going to take back to their planet was the proportion of one type and the proportion of another type. So again, the way we're going to structure this is we'll let P be the probability that the individual is one type. Now, we can call it either male or female. Let's call it female, but whatever name they give to it, that's the name they give to it. And we'll let 1 minus P be the probability that the individual is the other type. Okay? So what this alien wants to bring back to their planet is they want to bring back an estimate of P. Okay, so how are they going to do this? So what they're going to do, first of all, is they're simply going to observe people as they go by. Okay, so they're sort of taking notes, what goes by. And they notice that what goes by is they notice, you know, a group of females went by, and then a male went by, and then some more females, and then some males, and female, and male, and female, and female, and female, and male. And, you know, they're just taking notes, and then all of a sudden the buzzer goes off and they have to leave. So that's all the data that they've collected. And now the next step after observation, the next step in maximum likelihood estimation is to write down what's called the likelihood function, which is simply the probability of getting what you got. So we're going to write down an expression for the probability of this specific event. Okay, so we can write that down. We're going to write down, it's called the likelihood function, simply the probability of this happening. And now, again, I don't know what these probabilities are, but I know that the probability of this kind of person is a P. So the probability of observing a female is P. Now, because the events are assumed to be independent, what you see here doesn't tell you what you're going to see next. So because they're independent, when you see another female, it's P times P. and then another female, and then another female. So now you have the probability of observing 4 females in a row is p times p times p times p. Much like it is if you flip the coin 4 times, you say, what's the probability of getting 4 heads in a row? Because they're independent events, you can multiply the probabilities, right? And then you observe the male, so that's 1 minus p. And then you observe 3 females, and then 2 males, and then a female, and then a male, and then 3 females, and then 2 males, and then 2 females, and that's when the bell went off. Okay? Now, so I can simplify this a little bit. This is p to the, I have 4, 7, 8, 11, 13, and 1 minus p to the 1, 3, 4, 6. Okay? Now, I hope I did it right. But if I did, that would be the probability of getting what I got. Okay? Okay, now if this is the likelihood function, how can I find the value of p that maximizes the probability of getting this? In other words, what value of p, what value of p could I possibly choose that maximizes this likelihood? Now, how would I do that? Well, if you studied calculus at some point, you might say, well, one thing I could do is I could take the derivative of L, take the derivative with respect to p, set it equal to 0, and solve. And that would give you the value of p that maximizes the expression. But that assumes that you took calculus, and it also assumes that if you took calculus, you remember calculus. Okay, so that may not be the way you solve this. By the way, you may think that one of the things that you could do if you were studying calculus is you might think of taking the log of L, the natural log of L, because if you maximize the log of L, you've also maximized L. So sometimes it's easier to deal with the log likelihood and to take the derivatives of that rather than the likelihood. Okay, so that's why people typically work with log likelihoods, because they're often easier to work with, because you no longer have exponents and you no longer have products. Okay, the exponents come down and you have sums, so it's an easier function to deal with. But if you don't remember calculus at all, what could you do? Well, another thing you could do is you could say, well, look, I've got this function here, so maybe what I'll do is I'll just take different choices for p, and I'll write down the function is equal to p to the 13th times 1 minus p to the 6th, and I'll evaluate the function for different values of p. In other words, if p was equal to 0.1, then I would take 0.1 to the 13th times 1 minus 0.1 is 0.9 to the 6th. And I'd evaluate that. And then I would take another value of p, say 0.2. And I would say, all right, if it was 0.2, it would be 0.2 to the 13th times 0.8 to the 6th. So I'd evaluate it for different values of p. I'd evaluate the function each time. And then I would plot it. Here's p, and here's the function, p to the 13th times 1 minus p to the 6th. And I would see a function that rises, 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 and then eventually it begins to come down. And the point where the function is maximum is the maximum likelihood estimate. It's where the function peaks. Okay? So this is, in general, the way we do this is the idea behind maximum likelihood. So if we, again, you form a likelihood function, you either by taking derivatives or by trial and error, by different values of p, you find which value of p maximizes this function, and that's the most likely function of p, because it's the value of p that maximizes the likelihood. So when we come back after a break, we're going to talk about doing this for logistic regression model. Okay, so see you when the break is finished.